Let us see how Euclid figured out the area of a circle without knowing anything about pi. So what he did was he constructed a polygon inside the circle, what is called as a inscribed polygon. Now to begin with, he inscribed a four-sided polygon, that is a square. It's pretty easy to draw this because we just draw a diameter and another diameter perpendicular to that diameter. So we get the vertices of the square. Now, looking at this diagram, we know that the area of this square is going to be less than the area of this circle. To maintain consistency throughout, he focused on triangular areas. So he joined O, and let's say this is A and this is B, and he joined OB, and he figured out the height of this triangle. So now the area of this square is 4 times the area of this triangle OAB. Number of sides of inscribed polygon is 4. Number of triangles in the polygon will also be 4. One here, one here, one here, and one here. 4 triangles in the polygon. And height of the triangle AOB is equal to this. But as I mentioned, the area of the square is much less than the area of the circle. So to improve his area of the circle, he increased the number of sides of the polygon. So let's say with 6 sides, what happens? The polygon gets much more closer to the circle. Again, he increased the number of sides. He again increased it. So now what happens, as we are doing this, the area gets closer to and closer to the area of the circle. So area of the inscribed polygon is equal to 26.45 and dot dot. So now let me take you back and let's take it step by step. So now, as of now, it is showing the area as 18 with 4-sided polygon. From 18, it has jumped to 23, then 25.45, then 26 points. So as we keep increasing the number of sides, the area keeps increasing, but however much we increase the number of sides, because it is an inscribed polygon, it will always be inside the circle. That means the area of the inscribed polygon will always be less than the area of the circle. Okay? But what if we want to know that the area of the circle is how much less than something else? So for that, what he did was to not only inscribe a polygon in the circle, he also started circumscribing a polygon outside the circle or on the circle. So again, you end up with a similar kind of situation. We join this point and this point, we again end up with a triangle. So the area of the circumscribed polygon is 36. So inscribed polygon 18, circumscribed polygon 36. There is a big gap between these two. 18 to 36. So that means the area of the circle is somewhere in between these two figures. But as he keeps increasing the number of sides, see what happens. 18 goes to 23 and 36 comes down to 31. And we keep increasing the number of sides. As we keep increasing the number of sides, what happens? It gets very close to each other, but it will never get, or it will never become equal. Why? Because one is a circumscribed polygon and the other is a inscribed polygon. So the way we would look at it is that 28.199977755 is less than the area of the circle, and the area of the circle is less than the area of the circumscribed polygon. So he was able to arrive at a range within which the area of circle would fall, and how accurate you want this result to be, that would depend on how much exhausted you are by drawing all these polygons, so many sided polygons. So you keep doing it till you get exhausted. By the way, the actual area of this circle is approximately 28.27433388238081. This is using pi. And that is why, because pi is irrational, I'm using an approximate symbol. Area of the circle is approximately equal to this. So, and this figure falls between this and this. By the way, as of now, the number of sides this polygon has is 50. If I increase it to say 100, the gap will still decrease. Very interesting, right? So that is finding the area of circle using method of exhaustion. That's it.